Hello, everyone. This is Xiaoqian Yang. The topic I'm going to talk about today is comparing the speedup using OpenMP and MPI for image processing. And the contents we're going to cover today are problem description, solution, algorithm explanation, OpenMP implementation, MPI implementation, experiments and analysis. So what problem are we gonna talk about today? We all know the high frequency noise is a common problem in signal processing. Specifically in image processing, the actual underlying image might be obscured by the high frequency noise as it manifests itself as static. So in my project, I'll use a Fourier transformation to remove the high frequency noise from images so that we can get a blurred version of images. The operations are very expensive to compute normally. I'll use OpenMP and MPI to accelerate the computation. And also I'll benchmark and compare the speedup using multiple cores with OpenMP and MPI implementation. Knowing what the problem is, then how exactly do we remove the high frequency components of the images? Simply speaking, we need to pass the images through a low pass filter. First, use a two-dimensional Fourier transform to obtain the frequency domain representation of the image. Then 1/8 low-pass filter, as it's shown on the left here. This image shows the white squares and an eighth of the whole square on each side. This filter will be applied to the frequency domain image by multiplying the image matrix element by element. After filtering, an inverse two-dimensional Fourier transform is applied to obtain the resulting figure. The output figure should have the blurring effect compared to the original image. With the basic idea in our mind, now we can take a closer look at the algorithm. So if we are given a vector of complex numbers from x0 to xn-1, the vector says n. The formula for the yk elements of the transformed Fourier transform vector is shown in this equation here. With this formula, we can now compute the two-dimensional Fourier transform by first computing a one-dimensional Fourier transform on the row vectors, and then apply the same one-dimensional Fourier transform to the column vectors of the matrix. So with the two-dimensional Fourier transform, it is now very easy to apply a low-pass filter. The low-pass filter is simply a matrix of the identical size to the original image that is filled with zeros and ones. We can go back our slides and see the filter here. As we discussed here, this white square is only 1/8 of the whole square. And the white regions correspond to the values of 1. And black regions correspond to the values of 0. And here's the inverse Fourier transform, which is very similar to this on the left side. Given a vector of complex numbers from y0 to yn-1, also the vector size is n. The formula for xk element of the transformed Fourier transform vector is shown like this. So the final algorithm is read the image into 3 separate matrices. One each one representing red, blue, green pixels separately. And then we can apply the transform to a Fourier transform to each column to get a transformed matrix. And then we need to multiply with the low pass filter element by element. And then we use the inverse Fourier transform to each of the resultant matrices. After getting the results from the three matrices, we can put them together, and then we can get our final image. Now, let's dive into OpenMP implementation. We need to keep in mind that OpenMP has implicit memory sharing for communication among different threads. It uses lock and unlock for critical sections to guarantee consistency. So that is why we need to think about consistency and coherence while writing parallel programs. There are three matrices corresponding to the three color components. So we can do these three matrices one by one. We can implement the parallelism within each matrix computation. And each matrix computation will follow these steps. First, we need to get the rows of the image matrix and apply a one-dimensional discrete Fourier transform for each row using the discrete Fourier transform formula. Since we have several threads for the computation, we can distribute the task for each thread. If we assume there are n threads, then each thread is going to compute for total rows divided by n rows. And similar to process of taking row discrete Fourier transform, the second step is to use the obtained matrix from this step and to take the column-wise discrete Fourier transform. And the third step is to do the filter multiplication. This step is done element-wise. So we can still implement a parallelism. Since we know the filter has only 1 and 0 values, multiplication is the same as zeroing out all the parts that are in 0 region of the filter, and leaving the remainder unchanged. This would simplify the computation and speed up the performance. After doing the filter multiplication, then we can do the row inverse discrete Fourier transform and do the column inverse discrete Fourier transform. After repeating the above steps for the other two color matrices, we'll get the final processed image, which is a blurred version of the original image. Now, let's talk about MPI implementation. MPI is using the message passing style to communicate among different threads. During the calculation or execution, each process does not have shared memory with other processors. Instead, if anyone needs data from others, the data needs to be sent using message passing. This is the main difference from OpenMP implementation. MPI part is implemented by dynamic work assignment. So we will, a master thread is selected. This master thread is mainly for assigning and gathering work for worker threads. We assume the number of processes are no less than 2. So this will give us at least 1 worker thread. The working procedure of the master thread is dividing the rows uniformly to each thread and sending the rows to the corresponding worker threads. and then waiting for the worker thread's results of the Fourier transform on rows. And then similarly, divide the columns uniformly and sending each corresponding worker thread, then waiting for results. And then we do the inverse Fourier transform. When we divide the work for worker threads, we need to pay attention to the difference between rows and columns. For rows, we know there are 3 color channels, and the color image data has 3 channels, and the data layout is one after another. So we can just easily assume it as a single channel image with 3 times number of the rows. So we have total rows is 3 times rows, and the number of workers are number process minus 1 because we have a master thread. So when we divide work, if the module of total rows number workers equals to 0, then we can get the average rows equals to this total rows divided by number worker. If it's not equal to 0, then we can assign the average rows to equal to this amount. And we assign this amount to the first number of workers minus 1 worker thread. And then we give the extra rows, which is equal to this amount, to the last thread. For columns, because the address of image pixels is not continuous, it is impossible to send the raw image data directly to the worker threads. So here, a data buffer is introduced to solve the problem. We get the data used for each thread and reshape them as a special form, like shown here. The work later will be similar to dividing the work by rows. Okay, let's see the results of the experiments. The experiment was done on a laptop that has a quad-core CPU, which has a maximum of 8 threads available. I obtained the same output image for implementing OpenMP and MPI. And this is sample 1 feature. On the left side is the original image. We can see it's very clear, but this feature here on the right side is our resultant image. It is very blurred compared to the original one. And this is sample 2. Also, you can see the original image is very clear, and our resultant image is very blurred compared to the original one. Here is a runtime for OpenMP performance. The plot feature here is for sample 1, and this one is for sample 2. We can see from the numbers here, when the number of processors or threads increase from 1 to 2, the total time decrease a lot, almost decrease to half. And here's the runtime for MPI implementation. This plot is for sample 1 image, and this plot is for sample 2 image. One thing I need to point out is that total time here is the overall running time of the program, and the compute time here is measured by adding the computation time of the Fourier transform and inverse Fourier transform on rows and columns in the first worker thread. Thus, we assuming all the worker threads have the same computation time. Then the communication time is calculated by subtract the total time with computation time. And in the plot here, we can see the blue bars are for computation time, and the red bars, which is very small, but we can still see a little bit of red here. These are for communication time. And here are my conclusion. For both OpenMP and MPI implementation, the total time decreases as expected with the increasing number of processors, especially when the thread number increases from 1 to 2. The running time almost reduced to half. But when the thread number increases to a larger number, the performance doesn't improve as much as expected. And with the same number of processors, OpenMP is slightly faster than MPI because MPI has communication overhead. That's all I have today. Thank you.